Hi there and welcome to this video for Senior Physics on Motion. In this video we're going to explore the concept of relative velocity. So what is relative velocity? Well, it can be described as the velocity of one object in relation to another object. The velocity of that object may appear to be different depending on where it happens to be measured from. So for example, if we look at these two motor racing vehicles going past each other, from the crowd they may be going exactly at the same speed. Although as the black car is actually passing the white car, from the point of view of the white car driver, the black car driver is only going at a certain speed, which is a little bit more than what the speed that he's going. To the crowd, they'll all be going at an incredibly fast speed. To the white car driver, he may only be going at a slightly increased speed, maybe 20 kilometers per hour, slightly faster as he passes him. Why? Well, basically, the white car and the black car happen to be traveling at the same speed, so they cancel out. Let's look at the situation of this cyclist. Now, this cyclist, when we look at them from her point of view, will see the car moving off in the same situation as the black racing car against the white racing car. The silver car will basically go in front of the cyclist, and as a result, she will see that car moving at an increased speed from the speed that she's going. Now, relative to the driver of the car, what he will see or she will see is that the cyclist is actually moving backwards at a speed which is basically made up of a different velocity. So you can see that if you look out of a car window and you look at a tree passing you, that tree is passing you at the speed that you're traveling at, but in the opposite direction. If you happen to have a car which is overtaking you or is at the same speed as you and level with you, it's as though the two cars are not moving at all. If that car that you look out of the window at is passing you by, then they will be passing you by at basically an increased speed from what you're doing. Both of the vehicles can be cancelled out up to the speed that you're doing, so you're only looking at the increase in that speed. Now, trains can be a good example depending on the proximity of where you are. And we're going to be using the train scenario in this video to try and explain looking at relative velocity in one dimension and then relative velocity in two dimensions. Okay, so let's have a look at our train scenario. So here we have our train carriage. And basically what we're going to do is we're going to put a basketball in there. The basketball is going to be sitting on the floor of the train, and it's going to be stationary. Now, the thing is, and what we want to know is, we're going to look at it from an observer from outside. Now, what we're trying to work on is the idea that the observer can imagine that the ball is sitting stationary. It's almost as if we've cut the carriage in half so they can see the ball. Now, obviously, if the train is moving, then relative to the train, the ball is stationary. Why? Well, the ball and the train are moving in the same direction at the same speed. So as a result, their two speeds cancel out. So relative to the train, the ball is not going anywhere. It's staying in exactly the same position. However, when observed from outside, the observer will see the train and the ball moving in the same direction and at the same speed, hence the same velocity. So they will see the ball and the train moving together. So as a result, let's take a look at an example in one dimension, and we're going to use our racing cars again. So in this case, we've got an example where the black racing car passes the white car on a bend in the Grand Prix. The white car is traveling at 70 kilometers per hour, and the black car is traveling at 90 kilometers per hour. We want to determine the relative velocity of the black car, firstly with respect to the crowd, and secondly with respect to the white car. And hopefully this will demonstrate that although we know what speed the car actually happens to be going, their relative velocity will change as we look at the different scenarios. Now, the key thing to understand is that in this scenario, they're both going around the bend together, so we can rule out the concept of direction. We're only going to be looking in this case at the speed. Now, relative to the crowd, the white car is going at 70 kilometers per hour and the black car is going at 90 kilometers per hour. Our question asks us, what is the relative velocity of the black car with respect to the crowd? Well, the black car, according to the crowd, is going at 90 kilometers per hour because the crowd is not moving. They are stationary, so they see the black car go past them at 90 kilometers per hour. No real rocket science there. It's a very straightforward scenario. Now, where it gets complicated is, what is the relative velocity of the black car now with respect to the white car? So basically what we notice is up to 70 kilometers per hour, which is the speed of the white car, both cars are virtually stationary relative to each other. You don't see the white car accelerating away or the black car accelerating away up to that 70 kilometers per hour. However, the black car is actually going at 90 kilometers per hour. So as it comes alongside the white car, basically we can work on the principle that we're going to make the white car actually slow down to zero. And we're then going to say, so how much more is the black car going faster than the white car in this scenario? So as a result, what we have to do is take 90 minus 70. Now, that gives us 20 kilometers per hour in the direction they happen to be going around the bend. So relative to the white car, the black car is only moving at 20 kilometers per hour. This is because the white car is already going at 70 kilometers. So he sees the white car driver sees the black car driver passing them at 20 kilometers per hour more. Now the vector, basically, you can see where it says negative 70, is the negative 70 is converting our white car's speed to zero. So if you were to add those together, plus 70 minus 70, the idea is that the vector would actually get to zero. So as a result, by taking minus 70 away from 90, we then get what's left over. So the whole thing comes to zero, and then we see how much is more. So when viewed from the white car, the black car is going at an extra 20 kilometers per hour more. So that's fairly straightforward when we're looking at one dimension. The question then is, what's happening if we look at it in two dimensions? So let's go back to our train again. On our train, we've got our basketball. We're going to have our observer from the outside who is able to see the motion of the basketball in the train. Now the train is moving. Now in this scenario, what's going to happen is the person holding the basketball is going to throw the basketball directly up into the air. And we want to know, what is the observer going to see? Relative to the observer, what is going to happen to that basketball? Now the first thing to understand is that the basketball is traveling with the train. So it's going in the same direction as the train. However, it is also being thrown directly upwards. So the result is that as the train is moving relative to the train, the ball will be moving upwards only, because we cancel out the idea that they're both traveling in that same direction. But what will happen is, relative to the observer, the ball will move upwards and to the right following a parabolic motion, which means as the train catches it up, as they throw the ball in the air, the result will be that you'll be able to catch the ball. If you were, or the person who threw it will be able to catch the ball, and the train will catch up with the ball in the same motion. Now, why is this? Well, basically the ball has vertical velocity and it also has horizontal velocity. The vertical velocity is the velocity of the throw, and the horizontal is the velocity of the train. So we can put this together into a vector triangle to see the relative velocity which is observed by our observer. So basically what we end up with is the velocity of the ball relative to the train, which is going straight up, because the velocity of the train has been cancelled out because they're both going at the same speed. Then we've got the velocity of the train relative to the observer, so we know that the train is going to the side, and the result is that we get the velocity of the ball relative to the observer as a resultant vector, and it's the red line that we're going to find out. Now obviously we can find out our hypotenuse in this case from our right angle triangle by using Pythagoras and trigonometry. So let's look at an example. Let's put some answers to some values together and show how this can work. So let's say in the above example, the train is going at 100 meters per second and the ball is going at 2 meters per second. And we want to work out what is the speed of the ball relative to the observer. So basically we're going to calculate the size and the direction of the red line. So what we're going to do is make our triangle as we had above, and we're going to add in our various values. So we know that the train relative to the observer is traveling at 100 meters per second to the right. We know the velocity of the ball relative to the train is traveling at 2 meters per second upwards. So the instant that it's left, when the ball has left the hand of the person throwing it, what is the velocity of the ball relative to the observer? Well, we can calculate the magnitude of that red line by using Pythagoras. We can also find the angle using trigonometry. Now this angle is going to be theta. So let's find out the magnitude of the red line, which is basically going to be the square root of 100 squared plus 2 squared, which gives us an overall velocity of 100.02 meters per second. It's not massive, simply because the difference between the train speed and the ball speed is very, very small. So the net result is it's not going to be a massive triangle, which means that our angle is not going to be great. So let's find our angle of theta. Well, theta will be made up of tan to the negative 1, which basically is the opposite divided by the adjacent, and that comes out at 88.9 degrees. So it's only just off the vertical. So there's a slight movement upwards and down in that parabolic motion. So what do we get overall? Well, our velocity of the ball relative to the observer will be 100.02 meters per second at 88.9 degrees from the vertical. So as a result, it's going to be moving very, very shallowly in that trajectory. Okay, well, I hope that makes sense to you. We've now looked at relative velocity with respect to one dimension and also two dimension. Now, what I've also done is produce some exemplary videos to give you some more examples of how you solve a one dimension question and a two dimension. And then also in this post, I have put a worksheet of some relative velocities that you can go through and actually practice. Okay, well, thank you for joining me. I look forward to seeing you again. Bye for now.